Everybody sit down, get quiet. Okay, so I'm Claudio Ruch. I'm a doctoral student at ETH, and I will substitute Jacopo this and next week. So you'll have lecture with me for 2 times now. And just a short introduction, if you later come to our institute for a project, if you work on the go-kart, the autonomous go-kart, you will be in contact with Jacopo or Andrea or Julian. Then we have Ducky Town, so that's mostly Andrea, Jensi. And if you work on mobility topics, so not the individual vehicle, but a fleet of autonomous vehicles in cities, then that would be with me. So this is just quickly what I do. Okay, so today we have let me get to the big picture slide. So let me first state, today we have quite a difficult topic. So from a theoretical point of view, this is probably one of the most difficult topics in class. And this is why I have 2 key goals for this lecture. So I was thinking, what do I want to show you? What do I want you to take home? And my 2 goals are that for this new control method that we are going to introduce, which is called H infinity, with a funky H, I want you to understand why it has a value and why it works. So I want you to get an idea of the concept. Why have people thought about this control method? Why was it invented? And why is it useful? And secondly, and I want you to be able to apply it to a problem. So many of you will, follow another direction. So you will work maybe in more on the energy side, like thermodynamics, fluid dynamics, or you will be applied engineers later on, and some of you will continue with controls, but for everybody of you, I want you to be able to apply this control method to problems, to MIMO problems that you're going to encounter. And for the first part, so if you want to understand more about the theory, these readings are very good. So I read them extensively in preparation for this class, and I recommend you to do the same. For the second part, so if you want to actually carve out an H infinity solution to a problem that you encounter, you might want to read also other references, because these are very theoretical, high level, and so you could easily get lost in details that you don't need for actually implementing H infinity. And yeah, maybe that's an important little side note. So what did I do in the preparation? I was looking for a script that would explain me how to really apply H infinity. I wasn't so happy with these 2 references, and then I went back and I found the script of a former ETH professor, which stopped working at ETH maybe 15 years ago. And so what we do today is we bring up a topic into the MAFT schedule that has not been there for some time. So I think, Joelle, have you seen H infinity? No, you haven't. Me neither, during studies, after studies. So what we do today is we introduce something that has not been there for some time. Okay, so let's start with the big picture slide. 2 weeks ago, we've seen that if a system, a MIMO system, is not decentralizable, we have to go to MIMO control design methods. So we need these because there are cross-couplings in our system that we need to take care of. And Jacopo introduced, as a first example of such a MIMO design method, he introduced LQR. So that was 2 weeks ago. And LQR yielded a control law U of t that stabilizes the plant, and it minimizes a cost function that looks like this. So you all still remember that? Who does remember it? Okay, most. That's good. So what is in there? So we have one term here, which refers to the tracking error, and the second term is referring to the control input U. And as you see, both of them are in the 2 norm. So they are weighted 2 norms of these signals. So what does it mean? If we have the 2 norm of a signal, it's referring to the energy of that signal. So in this cost function, we have the energy of the tracking error and of the control input, which we minimize. What's important is that we saw that this control law takes this form. So it's state feedback. Opposed to what we did in control systems 1, we don't have a control law which takes Y, so the measured output as an input, but we use actually the state information X. What we saw next is that, well, LQR works very well. It's fantastic. We can place the poles as we wish, but we don't have X. So LQR control is actually not implementable. Does anybody of you did the hardware exercise? So you implemented LQR. What happened there? Well, in fact, you didn't implement LQR, but on the Dakibot, there was a state estimator that gave X estimate to you, and then on that, you did LQR. So in fact, you did LQG. So what we did is we introduced last week then state estimation. We don't have X, which is why we try to estimate it, which brings X hat. And if we take X hat and we use LQR on X hat, we have LQG. And LQG works very well. It guarantees stability. What's important is that it does not guarantee robustness. What does it mean? So this is a result which is not that new, but relatively new. I think it's about 25, 30 years ago it was discovered. So back then, people were implementing a lot of LQG. And it was applied to a lot of problems in industry and in academia. And then basically there was one paper coming out. It's a famous paper. You will certainly hear about it a few times in the study. And this paper, what it did is it took a system with 2 states. So a very simple system. I think it's a CISO system, even with 2 states. And it constructed a case where the LQG controller is stable, but a very small deviation of one of the parameters in one or the other direction makes it unstable. So what does it mean for you in practice? It means you do LQG, it is stable, but if there is a little uncertainty in your plant, a very small uncertainty, it might get unstable very quickly. So for many real-world instances, that's a problem, because you might be interested, for instance, if you design a controller for an airplane, to state that it is actually robust and it will not break down if you're a little bit out of the normal operating range. So today we will look at H infinity, and this is a MIMO control method that can be used to guarantee robustness. That's its purpose. This is an alternative to LQG, and the difference is we can guarantee robustness. Any questions for the big picture? Is the journey clear for everybody? For who it's not clear? Okay, very good. Then let's go into the recap, a bit more detail. Remember that with LQR, and the N matrix equals 0, we have an infinite positive gain margin. We have a negative margin of 6 dB, and we have a phase margin of 60%. So let's quickly remember the CISO case. So we have a Nyquist plot here, and we have the point -1 here. The plant is entering in here, and so what does it mean? It means that this angle here is 60 degrees. So we have a lot of gain margin, and we have actually quite a robust design. We also saw, I think it wasn't proved, but we saw that robust stability to additive model uncertainty and robust stability to multiplicative model uncertainty is present with LQR. So LQR in itself is a very good design method. As stated before, we have the problem that X is not available. And because X, oh, by the way, the slides look different, you've noticed. So the reason is that if I had worked with Keynote, then we would have no slides today. I'm just too slow, so I worked with LaTeX, and maybe I'll be able to paste it, but I hope it's fine for you to work in a different format this time. My apologies for that. Okay, so we need X of t. for LQR, but we don't have it. So what are we doing? Well, given an LTI system ABCD, at each instant t, we try to construct an estimate of the state, which is called x hat of t, by only measuring what's available to us, u of t and y of t. So these two things are what's known to us, x is not. Is there a question? No. Okay, and what we try to achieve is that the limit of this term, and in here, this is exactly e of t. So the limit of this term of the error should converge to 0. So as time goes on, our tracking error goes to 0, which means that x hat is x. So you remember that if we look at the dynamics of the error, so E dot would be x dot minus x hat dot, which is the same as ax plus bu minus ax hat plus b, sorry, that's a minus. I'm still training here my writing skills, but okay. Which is the same as a, we have the b that cancels, x minus x hat equals ae. So what does it mean? It means that the dynamics of the error, so E dot, follows the dynamics of the matrix A. And so if A is asymptotically stable, it would mean that E will converge to 0, which is exactly what we want. Now, there's a problem. Of course, we might have situations where A is not asymptotically stable. And the question is, what are we doing then? And the idea was to introduce, so we consider again this state chart. Actually, I'm used to my laser pointer, so I'll just grab that, so I can sometimes also point here. So well, that's not very suitable, huh? Okay, good. I'll keep drawing, but I hope it's readable enough. So what we have up here is the plant, or the process P, and at the bottom we have a computer implementation of that plant, which is the same, so the same A, B, C, D. And what we do now to compensate for the fact when A is not asymptotically stable is we introduce this L term. So you have ax hat plus bu plus L, y minus y hat. And of course, as you know, y is known to us. So we feed back the error in observation. So let's again look at the dynamics of E dot for that case. So E dot would be x dot minus x hat dot. Same as before, we have ax plus bu. So this is x dot minus, and then here we have additional terms in. And we see that, what is y? Well, y would be cx plus du, and y hat would be cx hat plus du. So the feed-through term with du cancels in here, and we have plus lcx minus x hat. We see that this in here is actually, again, the error. U cancels, and so we have a minus lce. So, by introducing L, we have found a way to change the dynamics of our observer and have different eigenvalues of this matrix A minus LC, which incorporates the dynamics of the error term. And so we can actually track faster and also track if we have an unstable system. Questions about this? Is this clear to everybody? Not too much? What is the question? It's clear? Okay. Very good. Okay, so what we saw also last time is that there is a principle that is called duality. So, actually, you will encounter that also in other parts of your studies. For instance, if you go on with mathematical optimization, you will see that also there is duality, and that's something that you will encounter all the time. And this principle of duality is that the control problem, so LQR, is what we've looked at, and here we've looked at Kalman filtering. So the control problem has exactly the same structure as the estimation problem. In both cases, we have an algebraic Riccati equation that we need to solve. So you see that here in the first column. And in both cases, we have then a resulting control gain or observer control gain K or observer gain L, which has part of the Riccati equation solution P infinity inbuilt, and which we then apply. Also, we have technical conditions which are related, and I haven't noted the exact transition, but I think it was B equals C transposed will bring you from the left-hand side to the right-hand side. So closely related, if you have understood one of these, you have also understood the other. Okay, let's get on with the last recap slide, and actually that's quite an important piece of theory, which is called the separation principle. So what are we doing? We try to, well, we've seen we have a control problem, which is concerned with the dynamics of X, of the state, and we have an estimation problem, which is concerned with the dynamics E of the error. So what we do is we put everything that we care about, which is the state and the error of tracking, we put it in this vector xe. And now what we try to do is we try to understand the dynamics of x and e combined. So the dynamics of E, well, they're obvious. We've done them 2 slides ago. They're simply E dot equals A minus LCE. Right? Objections about this? No? Should I throw the cube? I think everybody is still with me, so that's good. And the question is, now, what is the error of x dot if we take into account that we use an estimator to feed back to our LQR? Well, x dot is simply ax plus bu, which is the same as ax minus bkx hat. So here we have the LQR taking action. So u equals minus kx. Okay, now we have x hat, which is, we know that E is x minus x hat, so x hat would simply be x minus E. So we plug that in here, and so we can pull out the x, and then we get an additional term bke, right? So we plug it into the matrix, and then we have the final dynamics of x and E combined. Now what do we see? Well, this matrix here, let's call it M, has a structure that we call upper triangular. So there are non-zero elements in these 3 boxes, and it's 0 at the bottom left. So if we calculate the eigenvalues of this matrix, we will find out that it's nothing else but the union of the eigenvalues of the upper left box, so which is A minus bk, and A minus LC. So the eigenvalues of the combined dynamics are nothing else but the eigenvalues of the control problem, unified with the eigenvalues of the estimation problem. So what does it mean? It means that we can separate the control and the estimation problem. And actually, that's a very convenient fact. So what would be a case where we cannot separate it? It would mean that you design your controller, then you design an observer, but your design of the observer will influence the dynamics of the controller. So depending on what you implement, you might have to get back re-implement the controller, which then would influence your observer, and then you have a problem which is interconnected and which is much less simple for you to solve. Okay, so that's good news. And we can conclude here with the LQG design guidelines. How would you actually implement LQG? You're doing that on the DocuBot, I think. Who is still taking hardware exercise 3? That's very good, okay. Some of you, who is using LQG or tries? Nope, okay, you haven't started. What do you use then? I'm interested now. So 20 people do hardware exercise 3, nobody uses LQG. Didn't start yet, okay. Good. So how would you go on about doing that on the DocuBot? Well, first you do the control part. So you design the LQR controller and you place the poles of A minus BK. Once you're done with this, you go on and you do the estimation problem. So you would place the poles of A minus LC, and of course you don't have to do that on the DocuBot. The rule of thumb is that the observer should be about 10 times faster than the controller. So that's typically a good rule for getting a good performance. Yes? Okay, the question is, what does it mean to make something fast? So what I always do, so if I think about these problems, what I always do is I have the imaginary plane in front of my eye. So we have the real axis here and the imaginary axis here. So remember these plots from Control Systems 1. Huh? Now, if this is a pole and this is a pole, which one is faster? The one on the left, right. So if we have a system, let's say a first order system, step response, the one here will converge very quickly, and the one here will take longer to converge. So now this is the same in the MIMO case still, right? We just have multiple inputs and outputs. But in one case, the error would converge very fast to its actual value, which is not 1 but 0, right? And in other case, it would converge slower. So we have an error between x and x hat for a longer period of time. Is it clear? A quick question, just for the memory. So what happens if we get in this direction to our solution? Yes? Exactly. To the left, no, you're right, it becomes fast. If we get close to the imaginary axis, it gets slow. And if we go in the direction of the imaginary axis, we have oscillations. Huh? So always I keep this in the back of my mind. More questions? Yes? 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 Yes, this is correct, but there's a catch, which is A might still be unstable. So we've seen that the aerodynamics, so we've seen that E dot S is AE, if we don't have the part from the Leuenberger observer, so without the L. So if A is unstable, the error is going to infinity. Is it clear? I think I thought about this question too, and I think the way to look at it is we assume that our observer has exactly the same matrices A, B, C, D. And we know that this is, of course, not the fact. We have some model uncertainty, but we put it at another place in our modeling. So we will use it later. We will introduce it as uncertain, like as additive or multiplicative uncertainty to the plant. So in the observer part, we say, okay, let's get here. So here, we've always seen like ABCD on the top one is the same as ABCD on the bottom one. So we haven't addressed this case. Now, why? Because we say, well, in the estimation, we assume we don't do errors for theoretical, like to simplify the theoretical analysis. And then we introduce an uncertainty model of our plant, which we have seen in lecture 6. So additive or multiplicative uncertainty later on. Is it clear? I think that's the way to look at it. More questions? No? Okay, so then we should be ready to get started with today's class, which is this H-infinity approach. And we start with a little intuition. Huh? So the cost function for the LQR design has already been on the slide before. So it has these two terms here. Huh? Oh, let me actually highlight that. Can I do that? Oh, yes, fantastic. Very sophisticated. Oh, good. So it has these two norm terms. I've already stated if we have the two norm of a signal, it means it's energy. So what we do by minimizing this cost function is we minimize the energy content of a signal. The infinity norm has a different meaning. So the infinity norm for a signal would be its biggest absolute value. And so the idea is we take this cost function, we take the two norm out, and we replace it with the infinity norm. So what does it mean? It means we don't optimize the energy of the tracking error and the input, or minimize the error energy, but we minimize the worst case. And this will lead to a design with guaranteed robustness. Is this basic idea clear, to go from two norm to infinity norm? Okay. By the way, today we do H-infinity, and there is another class called H2 controllers, and LQG. Let me write it like this. It's not super clear, but LQG is an element of the H2 family. So you've seen LQG, an element of the H2 family, and today we do the H-infinity family. Okay? Good. As in LQR, LQG, we will introduce a mathematical machinery. So this is this algebraic Riccati equation to compute the solution. This time, this machinery is more complex. So I really tried to find a calculation that I can place here in class in these 2 hours. I cannot do that. So the general case of H-infinity, even in a very good script, is about 15 to 20 pages. And so it's not possible to simplify it, boil it down, so I can actually do the passages here in class. So what I want to do is I first introduce the concept of the general H-infinity problem in frequency space, because this is where it's easy. I will then show you one specific type of H-infinity, so one way of implementing it in detail. So we'll walk through the steps such that you understand what you actually see in the references. And then I will present the H-infinity solution and conditions, which are in state space. And as I said, the scope of these solution and conditions is beyond the scope of this class. Actually, we're quite daring, so because H-infinity is something that should be, well, it's almost a master topic, and to put it in the 4th semester is a leap. Finally, probably you will get lost. So in 1, 2, or 3, I will lose you. And I still want you to remember H-infinity as something useful. And that's why we do an example at the end. And it's an example, you will see it's a challenging system to control. It's something that I can explain here in class. And you will see that H-infinity will perform very well. And you will take that home as a message and remember it once you encounter a system that you want to control. Okay, so first of all, in H-infinity optimal control, we need to introduce a new structure. This structure exists also in the H2 case, but back then Jacopo was lucky because he could skip it, and I cannot skip it anymore, so I have to introduce it. So we do the same that we did with the robustness, is we pull out the controller of the total, the entire feedback loop. And what we have then is we have, on the left-hand side, we have W, which is an exogenous input, which is, for instance, the reference signal R, but we could also place such things as a model of the noise or a model of the disturbance there. On the right-hand side, we have C, which is called the performance output. And that's a virtual output signal that we only use in design. So you shouldn't see, if you open the Skogestad book, you kind of think, oh, well, see, this is something that I will actually measure and have in my physical system. It's not. This is a design quantity. So what could C be? We will see later that typically it's a weighted version of the regulated variables. Then we have U tilde and Y tilde, which is the measured output going to the controller and the control input to the extended system. Often, I think in our case, Y tilde will be E. I put here EG. So as example, Y tilde could be E and U tilde could be U. It could also be something else. Y tilde could also be Y, for instance. That depends on your implementation. I wanted to say something important. I just forgot it. Oh, yes. What's really important for you to remember is that what's here is not the process. So the extended system is not just the dynamics A, B, C, D, but it's actually the dynamics, the process, which are extended. So we blow this up, the ABCD matrices, we introduce more states, and then we place it in the extended system. Is that clear, this structure? Okay, so I will draw this a few times, so keep it in the back of your memory for today, Okay, so what does H-infinity control do? It stabilizes internally and externally the closed-loop system, and it minimizes this transfer function from W to Z. So we've seen here, this is the extended system. We are going from W to Z, and so we denote this as TWZ. So in S, for instance, state space. So we have TWZ infinity, which is the same as, another way of saying, supremum of overall frequencies of C, of the 2 norm of C over the 2 norm of W. So we look at ratios of 2 norms, and which is the same as the maximum singular value of this transfer function. Okay? So this is what we minimize, and we will call it gamma min. So whenever you see a gamma, this is the minimum value of this TCW. So what are we doing now? We take this extended system, TCW, and we incorporate constraints on regulated variables in frequency space inside TCW. For instance, on the tracking error E. We design TCW in a way that if TCW infinity norm is less than 1, then our constraints are met. Then we use the machine, so the H-infinity controller design machine. And if it has a solution for gamma smaller 1, it means that the corresponding controller will guarantee the constraint, will guarantee the bounds specified in the constraints. This is still a bit cloudy, probably, to understand. You will see it very clearly now. But I have to state it in a general fashion first. So TCW can be represented in different forms. So you as a designer, and that's your key part of work when you do H-infinity control, is you have to set up this extended system. And we present now one, it's the most simple of implementations of TCW. But keep in the back of your mind, there are others. Questions so far, or is the general idea clear? Yeah, I lost a few people, maybe 20%, but it's not as much as I feared. Okay, so we will go now into the design of TCW. Okay, we'll look at how would we set up the extended system. So we remember this feedback control loop that goes from R to Y. And we consider now a few signals of interest. So for instance, we remember, okay, we have the error here, right? What is going into our controller. So this is the tracking error. So of course, this is a signal of interest. I've stated it in a big variable to make sure that it's clear that we are in frequency space. Now, I mean, I don't have to do the calculations, I guess. We can say, well, E is nothing else but R minus Y, which is the same as R minus, and now we take out this, C and P applied to E, and so we can say, well, okay, E, so let me erase that. I don't do the calculations for all, just for some. So we can say that identity matrix plus PC times E is R, and so E is equal to I plus PC inverted R. And of course, remember that this one here is the sensitivity S of S, huh? I think that's still clear. So we see the same in here, right? So we have, oh, well, that's not possible. Okay, that's too much. Back. So we see here, okay. So we can repeat that, and then we get this structure, huh? Quickly, why are we interested in E? Because it's the tracking error. It tells us how much difference there is between reference and measured output. Why are we interested in U? Anybody tell me, please? Why do we have U in the formulation? Yes? Yes, and why do we have it in the cost function? Yeah. Exactly. So if U is very big, Jacopo was mentioning the example of the rocket. So if U is very big, we use a lot of fuel, right? And if it's small, we use less control input. And we also have Y in there. Now this is stated. So we have this term here, and we have Rn on the right-hand side. So we can already see this is getting, oh, I'm still with the marking, okay. So this is getting into the direction of our Z, and this is our W. Now, what's important to see here is that the first column is the same as the second column, right? Just we have a minus sign. And we know that the norm is homogeneous, so minus is the same as taking out the minus. So in fact, we see that if we solve the problem for the first column here, then we don't have to look at the second column because it will just be the same, right? As soon as we take the norm, the minus doesn't play a role anymore, which is why we take out n for the H infinity design and we just consider the reference R and one of the columns. Because we don't have more degrees of freedom if we consider both. Okay, now we are still not there because now we have a problem. So you remember, for instance, let me get back so quickly. So we have S of S here, huh? So E equals S times R. And you remember from control systems 1, what S of S should look like is typically like this, huh? Now, what is the problem if we optimize the infinity norm of this function? What happens? Can somebody tell me, what is the infinity norm of in this picture? Just by intuition. I know it's not easy, and actually it's hard to compute infinity norms of systems by hand. But where do you see the infinity norm of a transfer function? Yes? Maybe it's right, but I didn't understand what you said, so I'll try to answer it. So it's this, right? So it's the maximum value of this transfer function. Now, what is the problem if we just optimize that? We have no clue what's going on here, right? So in this area here, S of S could be anything. So if we optimize the infinity norm of this thing, it will push down on the right-hand side, but here at low frequencies, we have no clue what's going on. And this is why we have to introduce these weight functions. And I call them WE, WU, and WY. So we introduce these weight functions, and these are also dynamic systems. So actually, let me try to change the color. I'm adding steps. So I could, for instance, say, well, okay, I have, where's the sensitivity? It's multiplied on E, right? So I have WE here, and I make it very big here, but smaller over there, right? So what does it mean? If I multiply these two, I bring everything to the same level. So I can give a weight to some ranges of frequencies, and then it makes again sense to optimize or to minimize the cost function in an infinity meaning. Who has not understood that? Okay, why? What's not clear? Yes?
Well, when we apply this weight function, we will bring all the signals to the same level. That doesn't make sense for you, because then it's like it will always be the same value as after applying the weight.
Yes, okay. So the problem in considering it like this is we can still change. So S is something that we change in the design process. So remember that S is one, oh sorry, that's the CISO case, 1 plus, so that's wrong, this one, okay, so, okay. So remember that this is 1 over 1 plus PC, so we have the process in there, but also the controller. And the controller is determined by the H infinity scheme. So we change this S in the design process, so we can put it up or down. But what we try to do is that we have a similar weighing of all the frequencies. And therefore we optimize over all the frequencies and not just a small part. Yes?
Can you just quickly tell which matrices you multiply the W matrices to?
Yes, you see it here. This is coming from here. So if you want to compute U as a function of R, you will get that it's CSR. Clear? Okay. Good. I repeat this one more time because this is a very important concept, and then we do the break. Okay? So, okay. If I optimize, if I don't have the weight function, then I have, for instance, S of S, which would have such a shape, and the infinity norm will only consider the part with the highest magnitude. So if I optimize, I lose the possibility to influence the part where it's lower. And in the case of the sensitivity, this would be the low frequency ranges. This is why I take the signal and I multiply a weighing function to it, which is also a dynamic system. So we formulate it in frequency space. And by doing so, in the case of S, we have now the red weighing function, which is big at low frequencies and small at large frequencies. We are able to make sure that we optimize not over just one part of the frequency space, but over the entire frequency space. And this is why these weight functions are absolutely essential. Okay, now we're done. So here we have E, and the performance output is now E times the weight function. So we take the previous slide, we multiply WE, WU, WY, and then we get our extended system TCW. Okay? And we have the performance output is the extended system times the exogenous input. Okay, so who has still not understood this? Just for my reference before the break. Ah, it's a bit better. I went from good. Then we do a break. We continue at 9:15, and then we will go on with this extended system. Okay? Everybody, find your space. Get quiet again. Okay, so there was one question which was asked several times in the break, and I think it's a fantastic question. It's really good, and that's why I want to quickly explain what the question was and what it means. So basically, people asked, well, what are these WE, WU, WY? And I would like to explain that by explaining what's the difference to LQR. So what were the equivalents of WE, WU, WY in the LQR case? Anybody tell me? Please. Somebody should know. Somebody asked the question. So, yes. Say again? Q and R. It's the, Q and R matrices, right? So the weights in the objective function in the LQR problem formulation was Q and R. Now remember, especially those who did the hardware exercise, what can we influence with Q and R? Please. You want to? Oh, looking away? No. So Q and R, we tune them. What do we influence? We not continue before we have already one hand. Yeah, please. How much what contributes to the total cost? Okay. So in LQR, what we did is, it was Q and R, I think. Q, R, make an influence on the tracking error C and U of T. So how in an LQR setting, well, no, confused? Okay. How in an LQR setting would you take a direct influence, for instance, on the sensitivity function? Can you do that? No, right? Because if you tune with Q and R, you will tune Z and U, and okay, you can do that in MATLAB all the time and then look at the sensitivity, but you cannot directly impose constraints and conditions on the sensitivity. Here we can, right? So if we make WE smaller here, so we have this zone here, we make WE smaller, then we say, well, okay, the sensitivity should be smaller in that frequency range. So we can, in the design, directly influence sensitivity, complementary sensitivity, and possibly also other signals that we include in the TCW. Is that clear, the difference? To whom it's not clear? Okay. A second important point that was stated. Somebody asked, well, there is this waterbed effect, so S plus T equals 1. Yes, it still exists. What you introduce here are upper bounds. And you will see, try it yourself in MATLAB, if you introduce bounds which are too strict, then you will not find a solution. So you don't make an equality condition on your problem, but a smaller than condition, right? And so what the optimizer or the H-infinity machine tries to do is it tries to find a controller that satisfies all of this, but if you are too greedy, right, you make this sensitivity super small at small frequencies, then you will fail because there will be no solution. So, okay, good. So now let's get from here to the extended system. what are we doing? Well, we set W equals R. We set, okay, Y, remember this, huh? So we have this in the back of we have the extended process. W comes in, Z goes out, and then we have a Y bar here going to the controller, and we have a U tilde, not bar, sorry, getting back. So we set Y tilde as the error, U tilde as U, so the error goes here down to the controller, which feeds back its control input U, and now we see that this here, the big square here, is exactly our this is our system from Z to W, from W to Z. Clear? I see one confused face, so probably there is others because you are correlated. No? Okay, no questions? Okay. So we have this extended system, and now we take it out, and we look a bit in more detail at these constraints before we go on. So how would we in practice shape the constraints? What we do is we think about S hat, T hat, and R hat, which are acceptable upper bounds for the sensitivity, the complementary sensitivity, and the transfer function from the reference to the control input. Okay, so we say, well, the sensitivity should be in that range, complementary sensitivity should be below this, and maybe my influence of the reference, of changes in the reference to U, should be also below some value such that my U doesn't get too big. Does anybody remember? We looked at this, so you know what a good sensitivity transfer function looks like. I think it was lecture 5 or 4. We did this also in Control Systems 1. So you know what these transfer functions should look like, so you can formulate bounds. Huh? So for instance, before, as we said, you can take sensitivity, you say, well, it should be below some value for low frequencies, and then you have another bound for high frequencies. What we do now is we set the weight functions as the inverted upper bounds. So the upper bound on the sensitivity is S hat, and we set WE as S hat inverted. So what's in there then? We basically have S hat inverted times S, and we take the infinity norm of it. What does it mean? It means, let me draw that here. So let me change the color. So let's say this is, I changed the color too quickly. That was not a good idea. So S hat inverted. No. So that was wrong. So there's one inverted that shouldn't be there. Okay, I'm too confused with these colors, so I'll just talk. So this is S hat here, huh? And let's say we have such an S. Now, what we see is that inside the brackets, this is just another way of saying, and now I make here a CISO, S divided by S hat. And what we see, well, where is this constraint satisfied? Is it satisfied here in the first area? No, because S is bigger than S hat, so it means that the ratio is bigger than 1, so we're not happy. Here, the ratio is smaller than 1, and then again bigger than 1. And this is exactly the principle. So we put these bounds in here, and then we know that we have this relation. And so if the H infinity problem has a solution for gamma equals 1, it means that the specifications for all the transfer functions are satisfied. That wasn't probably a brilliant way of explaining it, but I did a few jumps there, but to whom it's clear, this correspondence. Okay, somebody, it's clear to nobody, so a specific question maybe to help me a little bit. Where did you get lost? Where did you get lost? At the plot, yes?
I think you said that the norm of the project, you want it to be smaller equal than gamma for the small gamma, right? So smaller than 1.
Mm-hmm.
But then H infinity prime has to be for gamma equal to 1. Like where is the correlation?
Okay, so what we have in the big formulation here, we just have any gamma, right? Now we replace this and we set 1. Okay, that's the first idea. So we set 1, and then we use here, oh, this is not what I wanted. Can I just zoom to page? Okay, so then in here, instead of WE, we put an acceptable upper bound, right? Which is exactly the red function here, red transfer function. Now, if the S of S that we can influence with the controller, so inside the H infinity machine, we will change S of S. Now we see that if it's up on top of the red function, then the ratio of these two, so S divided by S hat is bigger than 1, but if it's below, then the ratio is smaller than 1. Which means, and now let me erase this again, we take the H infinity machine, we solve the problem, and if it's feasible, we get some gamma. Now, MATLAB or another software will tell you what the gamma is, so it will say gamma is 5. But then you know, if it's 5, then we haven't met our constraints. If we put it in this way, it needs to be smaller than 1. So you need to retune, you need to change a few things, maybe allow bigger control inputs, and run the machine again. So did that answer your question? And less confusion over there? Yes? Okay, good. Now, yes, first here, yeah.
Sorry, so what we're trying to achieve is just to have an S always bigger than S hat.
Yes. No, the other way around.
Sorry, yeah.
The other way around, yes. Exactly. We set an acceptable upper bound, and then we try to have S below that. There, yes?
Why do you have to make these boundaries like it has to be one more strong?
Okay, so for instance, remember what is S, right? It's the transfer function from disturbance to output. So typically you want to have it small at very small frequencies, below the crossover frequency, because you don't want the disturbances to affect your output. So that's why you know that it should be small there.
So it has to be smaller than 1.
Yes, essentially, but maybe even smaller, because you don't want any amplification of disturbances. And then you also know that T, for instance, would state how the noise affects your output, right? And then you know that noise is at high frequencies, so you set a limit on T at high frequencies. Look at specific, yeah. Yes, so the boundary is always 1 because we compare the actual transfer function with an upper bound, right? Yes?
Like the gamma which is like smaller than 1.
Yes.
The problem is still the solution still satisfies the specification, right?
Yes, exactly. If you...
It just, yeah, so what you bullet point H main point has solution for gamma cannot be smaller, right?
It can be smaller, yes, absolutely. As long as it's smaller, it's fine. Okay, so for some of you, I would recommend look at specifications again. So maybe look at the slides from Control Systems 1 and 2, where we stated what the loop transfer functions have to look like. That's important, and I see that it's not too clear. But we know what S of S and T of S and all these other transfer functions should look like in a good system. And now we have a way to impose that on the MIMO system. I cannot do the ratio here in the MIMO case, but it's exactly the same, because if we have a maximum singular value in here, which is smaller than gamma, then the minimum singular value of the inverted transfer function will be just 1 over sigma bar. So I cannot expect with this WE that it gets reduced by more than this factor, so it's exactly the same, just a bit more complicated. Okay, so I'll go on. I think it's clear to maybe 50% of the class, or yes. So let's go on. I can answer some more questions about this later, but I want to get to the example as well. So the problem now is, this is state space, frequency space. We were able to model the system. We could impose constraints on S, on T, and on other transfer functions, but we cannot find the solution in frequency space, unfortunately. For that, we have to move to state space. So MATLAB and other software will ask you for a state space representation of the extended system, which is why, and I want to show you these steps, we need to make an effort to put our design here, which is very intuitive and very understandable in frequency space, we have to move it to state space. And this is where part of the mess starts. So first of all, we have these here in frequency space representations. So we first need to put all of them to state space, right? So you remember that a LTI system, to go from state space to frequency space, we have this formula. And so similarly, for instance, using the controller canonical form, we can find a state space representation for these transfer functions, okay? So we do that. And then we set up the extended system. And now you have to be careful, because WE, WU, WY are dynamic systems. They're not static, but they're dynamic. So it means that they have a state in there. So we need to introduce these states, XE, XU, XY, and they have, of course, a dynamic as well, right? So instead of having our TCW in frequency space, we now have a, call it P extended, so we have a state space representation of our extended system, which includes the original state of the plant and the state of all the W's, and which has as input what is coming from the left-hand side, so W and U. So remember this, huh? Remember this chart again. Okay, I need to keep track of time. So we have WZ, and then we have U here, or we called it, and Y, so, or E, sorry, in that case, E. So we have two inputs, W and U, and we have what's measured is Z plus the error which is coming out on the right-hand side. So this is the extended system, nothing complicated, but we need to move it to state space, okay? Now, how would we practically do that? I want to give you one example so that you understand how it's done, and then you can do the rest at home or a bit, it should be clear afterwards. So remember that an LTI system, which we have here, has a flowchart representation which is like this, huh? Okay, so now how would we find XE dot? To whom it's not clear what XE dot is now? Okay, it's clear to most, that's good. So we say, well, what is it? It's simply A times XE. So here we have, let's say this is UE, this is YE. So here we have XE. So it's A times XE plus BUE. So which is A times XE plus BE. And now what is coming in here at this side? We look back. So here, that's this signal, right? Which is E, which is nothing but Y minus R. Okay? So we put that. Oh, well, there's a typo, huh? R minus Y. It's R minus Y, huh? Okay, good. Not a typo, but I said the wrong thing. So it's R minus Y, which is the same as W minus, now what is Y? It's Cx plus du. We know that from the process. Now we see that we have a term with X, a term with Xe, a term with W, and a term with U. So we can put everything together and we get 2 rows of the extended system. Clear? Who has a question? No? Yes?
Why is it XE and not XE dot? Because we're integrating it afterwards.
You're right. This is Xe dot. I'm sorry. Yes. My bad. Okay. We do the very same for the output equation. So we say ZE, so which is just YE, is the same as C times XE plus D times UE. We put in all the stuff and we get another row of the extended system. Okay? I'll skip this, so we save some time. What we have at the end is this. So we have 4 matrices, A extended, B extended, C extended, D extended. And we see that A, so the original A, is just one little part of this matrix. And the original B is just one part here. What's really mean now is that in literature, you will find this. So you see here, this is A extended, so which is the same as here, right? In literature, you will find it in this format or this format. So basically, you will see that, oh, I have A here, and then you will lose a few hours to figure out that this is actually not A, but something much bigger. So take care of this. This is where the books, the references typically start. Okay. So what have we done? We just went from a frequency space representation of the extended system to a state space representation. Okay? Why did we do that? Because we need state space for the H infinity machine. Questions at this point? Yes. No, it would be, you would find it in the book often like this. Oh, that's not good. Like this. Exactly, yes, exactly, yes. And so your job as an engineer, or key job, is to design these extended systems, as we just specified. Good. I'll go very quick here. Basically, now we have the extended system, and we want to throw it into the H infinity machine. This is something which is solved in software. You'll not do it by hand. And so there are a few conditions. They're stated here. Some of them are intuitive to understand. Others are hard to understand. I'll skip them. But basically what we see here, for instance, A, B2 needs to be stabilizable. What does it mean? Well, basically, this A together with this vector here needs to be stabilizable. We kind of intuitively understand that if this is not met, then no controller, like if we have states which are unstable, but we cannot access them, then we cannot find a controller that guarantees any limits, right? So this is clear. Same for detectable. And then we have a few other conditions that I won't go into detail. As I said, the general proof for this H infinity machine is quite large. Anyone who's interested to do it, you're more than welcome. I can give you the reference. I found a version which I understood, but it's a lot of pages, and it wasn't very an enjoyable experience. Yes? That's A extended. Yeah, you see, even I get confused with these things. So. Okay, so it's not an enjoyable experience, but what I want to show you is I want to show you a very simplified case. So if we have these simplifying assumptions here, then we can see that then it, like these, you know, a lot of pages boil down to just some lesser pages, and we see that a controller, that there is a relation to what's known to us, to the LQG. We also have Riccati equations that appear. So a controller C of S, such that T CW infinity less than gamma exists for gamma bigger 0, if and only if this Riccati equation has a solution, and this Riccati equation has a solution, and there is a condition satisfied on the two solutions y infinity, x infinity. The only purpose of this slide is to show you that this is just a more complicated case of what you've seen with LQG, and at the end of these many pages you will encounter Riccati equations. Okay? I forget it again. I just want to say one more thing which is important for you to understand also the software, which is how would you typically find the solution? Well, it is not possible, or it's hard to design software that actually optimizes or that actually spits out the optimal gamma. So what is done is called a bisection method. What does it mean? It means we have gamma here, and we start with the lower bound gamma minus and gamma plus, and we choose gamma minus equals 0, so something that is quite impossible, and gamma plus we typically choose as the H infinity norm of the H2 optimal design. So this one is feasible, right? And then we would reduce this interval here in the gamma space by always taking half. So we have another gamma here that we try, and then if it works, so if it's a feasible H infinity problem, we reduce our search to this space. So we then try the one here in the middle, right? If it works, we go to the left space, but if it doesn't work, we go to this space. And so we keep converging to a smaller and smaller area for gamma until we have met the tolerance that we specify in the software. And typically this is a parameter you would give to the H infinity engine to find the solution. Okay, so time to wake up again. We go into understandable material once again, and I'll propose this recipe to you, and afterwards we'll go into the example. Okay. H infinity is a powerful method, so you should definitely remember it because it's one of the most successful ways of implementing MIMO control. The other way that you will encounter later on in your studies is called model predictive control. There you also have difficulties because you solve optimization problems during the execution of your system, and you have to make sure that these always have a solution, they shouldn't be infeasible, and there's a lot of steps to take there. It's also quite complex. With H infinity, you have the advantage that you are still in frequency space, so you still have a frequency space representation of the controller, which gives you some other methods of understanding that maybe are not as easily available in other methods. So remember it, okay? What are you doing? We just repeat the steps. First, you get the model of your plant. You choose the measured outputs and control signals U. And very important, understand the plant with analysis methods. We will do that in the example that I will just do now. Very important, is it stable? Is it not stable? What are the difficulties? Is it delayed? Is it not delayed? What are there nonlinearities? What is happening? After this, you choose an implementation scheme for the extended system. So that's what we've done in the past couple of minutes. So define W and Z, and you derive the transfer function in frequency domain, right? So be aware of what this is. Then you design these weight functions, which are basically the equivalence of these Q and R matrices in LQR. And you put everything to state space representation. Okay? Then maybe you want to evaluate the conditions of the existence, but you can also try to skip that initially because the software will complain anyway if you don't meet it. And then you turn on the H-infinity machine and you see what gets out. And then typically the controller that gets out has quite a high order. So you will maybe find terms of S to the 6, S to the 7. So you might want to reduce the order a little bit for the practical implementation in digital control. So these are the steps. Follow that recipe, be very concise in how you design it, and then it's something that is very useful. I would be delighted if somebody could do that on a DuckyBot. So it would be absolutely fantastic. If anybody is interested, please try. I'm happy to support. Okay, so for the next 14 minutes, we will go through an example, which is a CISO example. I just do it for simplicity. Be aware that in CISO, you also have other methods available, but in MIMO, you don't. So in the MIMO system, H-infinity still works the same way as you will see it now in this example. Okay, so what's the system? It's from a script, this ETH script I found, and it's a servo motor. So we have, this is a translational servo motor, so this black bar we have over here is moved up and down, and x1 is the position of the servo motor, x2 is the speed, so x1 dot, and x3 is an internal state, which is called the armature current. So it's the current flowing through the coils inside the servo. We measure the position, and we can control the armature current with a reference U, okay? We want to have an approximate bandwidth of 100 radian per second, and we want to have a robust design, okay? Good. Well, first step, and this is a part of the pain you encounter in actual applications. You have to model everything, and you will get to this LTI model with matrices A, B, C, and D. And I also placed some parameters there so that we have an idea of what the units are and if our results kind of make sense. Then we know that, well, this is the transfer function. We simply computed C times Si minus A inverted B plus D. So we get this transfer function. We see, okay, we have 3 poles. And what we see is that 2 of them are stable, and 1 is unstable. So how to interpret the epsilon? I introduced the epsilon, or this example introduces the epsilon to make your life hard. The physical interpretation is that this servo motor has is a little loose, right? So you go to one position, but it doesn't stay there. It doesn't stay at this position. Huh? That's the way I interpret it. Okay. So what are we doing first? We use any possible design, or like the preferred design method that you want to get an idea of what's happening. My favorite is root locus. I absolutely love root locus. And the reason I do so is because once you get experienced with it, you can very quickly understand, in the CISO case, what a plant is looking like. So what are we doing to get the root locus? We place the poles. Who does remember root locus, by the way? Almost all of you. This is fantastic. Okay. So we see that 1 is here in the right-hand side. The others are there. We know that for no control gain, the closed loop poles are on the open loop poles. And we now draw how they move if we increase K, right? So along this line, we have k going up. So what we see is this is not part of the root locus because the angle equation is not satisfied. Then this little area here is on it. This is not on it. And the left-hand side here, let me change that to blue actually. Oh, that was wrong. Okay, so this is on it. This is on it. Then we see there's 3 poles but no zeros. So, which means we have 3 asymptotes, so we can compute the angles, and we know that they're like this. And then we already understand how it moves, so as we increase the gain, the pole here will get to the left-hand side, stay in there for some time, and then it will again go to the right half plane. So what does it mean? It means if I have a very small control gain, I have an unstable closed loop system. If I increase, I get into some area of stability. And if I increase too much, I'm again in the right half plane, and I have an unstable closed loop system. So what you see is, this is not a trivial example. You see it already, right? Because, well, you have to find some zone for which k will result in a stable closed loop system. This is called conditional stability, or condition stability, by the way. Okay, clear? Do we have an idea of what the system is working? Yes, we do. So what are we doing? Well, the numerical values are a bit ugly. I beg your pardon for this. It can be done more pretty, but not in the amount of time I had. What's important is we design S hat. So S hat is here. We say, well, we have an upper bound at lower frequencies. We have a bound here. So we just design a transfer function that incorporates these bounds. So we want the sensitivity to be here in that area and to be below that here, right? So we do that, and then we select WE. We select to be simply, where is that? WE is just, as I said, the inverse of S hat. And as you see here in the Bode plot, yeah, it's just swapped, right? Questions so far? No? Okay. We do the very same for T. I didn't place so much emphasis on this one. That's what gave me a good result. I focused mostly on the sensitivity on the bounds. Oh yeah, by the way, you see also we have 10 to the, yeah, what we see is here is omega c, so the crossover frequency, and T has an upper bound which is still high enough here, right? So if you have your T like this, then you will not meet the requirement for the crossover frequency, of course. Okay, we do the same for U, and there we place quite stringent bounds. So we say that we want to limit how big the control input U can get if we have a certain change in reference. So this is specified here. And then we go through all of these steps. We first do transform everything from frequency space to state space. So we have to solve a realization problem here. And I made sure that all of these are just one by one matrices. In the general case, they might not be. So you will have a bigger matrix. So we do this. And then what we get, feel free to try that, is we have an extended system with the model parameters in there. So we see that this is A, right? And here we have AE, AU, AY. And here we have B. Here I think we have D. And here existing C, right? So we get an extended formulation. And now, I try to reduce my explainings to 2 lines of code. So you do all of this, and then you use your preferred software to the H-infinity problem. I used MATLAB, although it's not my preferred software. And then the 2 lines of code which will turn on the H-infinity machine are just these. So we say, well, P extended is a state space representation of these 4 matrices, which you have derived in a long and painful process of design. And then we put this extended system into the H-infinity solver, and we specify the number of inputs and outputs. So here, this is a CISO case, but, and I want to emphasize that, this still works in MIMO. And that's one of the key reasons for its existence. What we'll get out is a controller C, so which is a dynamic system. We get a closed loop. We get our achieved gamma. So you want to check if this is smaller than 1, and fewer informations, right? Questions on this? I was fast in this example, but it's nothing new. You've seen it before. Huh? Okay? Well, what are we doing then is we check how it works. And what I try to plot here is the response to a 10 centimeter reference. So the reference would be like this. It would go to 0.1 meters. Basically, we tell the servo moves 10 centimeters up. Okay, honestly, I didn't try to make the PI bad. I spent maybe 10 minutes to tune it, and this is the best I could get out, right? Of course, this is not the preferred method. You would use loop shaping, but see here, these are 50 seconds. We have quite a bit of oscillations, and at 50 seconds, it's more or less stable, right? And the amplitude, so this is in ampere, is also oscillating a lot. So quite clearly, this is not something that you enjoy, right? And it also shows, we know that if we get closer to if the phase margin gets smaller, then we have less robustness in our design, right? So this is also a statement that we are close to instability. If something happens unexpected, if the model changes or whatever, then we might get unstable. With H-infinity, after 5 seconds, we are converged, so it takes actually just 1 second, and we manage to have a control signal which is still like decently small, so we don't exceed 1 ampere. So I think this comparison is a clear statement that this method is quite interesting for controlling difficult systems. Questions here? Yeah. It's small on the right side, yes, true. So this is why I said we go a bit higher here, but not too high, right? If you play around, if you design this in MATLAB, you play around with it, then you can also get solutions which converge much quicker, so in 0.01 seconds, but then your current will go up to a few thousand ampere, which is probably not what you want, because you then don't have a servo motor anymore afterwards. So important here, we look at the body plots, and what we see is that in the PI case, we have a ridiculous phase margin of 2.89 degrees, whereas in the H-infinity case, we get to 63 degrees. So we have a fantastic phase margin. This is a very robust design. Huh? Okay, and what is the underlying magic? So why is the H-infinity scheme able to get such a function? Because it's quite high dimensional, so we can exactly tune when to put a lot of control input and when less, and with the PI we cannot tune it so well. We can also plot the bounds, so we have gamma here, and then what's inside the TZW, so the weight times the sensitivity here. So we see, okay, we are not at the bound in this case, and we see here we approach the bound, right? So what do you want to do if you want to get a better performance even? You should allow higher U, and then you can get even better, right? Okay, we're at the end. Give me please 1 minute, that would be much appreciated. Take home, LQG cannot guarantee robustness. H infinity can guarantee bounds on regulated variables, such as the sensitivity S of S. If you want to implement it, your biggest step is to model an extended system TCW with a performance output C and exogenous inputs W. Remember this, H infinity design will minimize TCW infinity, which is the minimization of the worst case scenario. This is what it does. And keep in mind, have a very well defined structure, put everything in a documented way, step by step, then you will succeed, because it takes a lot of steps to actually complete. Next week, we'll do a very exciting extension. So we have opened the MIMO dimension, so multiple inputs, multiple outputs, but we were always in linear space. And next time, we will get back to Control Systems 1, lecture 2, slide 1, or something like this, where we had this assumption, x dot equals f of xu, and we said, well, we consider linear f. Next week, we'll drop that. So we'll see what happens if we have nonlinear f. Okay? Thank you, and have a good weekend.